In this video, we're going to look at writing exponential functions and using them in real life situations for half-life and doubling. So let's just take a look at reviewing how we actually write exponential equations when we know the initial value and also the rate of increase or decrease. So remember, we'll plug it into a formula similar to this, where you have the initial value times 1 plus the rate to the time. So we'll have P of t equals the initial value. And so in this case, our initial value is 3. And then we'll multiply that times 1 plus the rate. And just be really careful when you plug in the rate that you actually do the decimal, not the percent. So remember that the decimal version of 33% is 0.33. So make sure you plug in 0.33 here and then to the t power. So now you can just simplify this inner part of the parentheses. So we won't be able to bring the 3 in since we've got this exponent. So we've got 3 times and then just add 1 plus 0.33. And then we'd have 1.33 and then to the t. And remember, this one was adding because we had an increasing rate. Then for this next one, so we'll do P of t again equals the initial value, which in this case is 18,900. And we'll multiply that times 1 plus our rate. Well, and actually in this case, we'll be doing 1 minus our rate since our rate is decreasing this time. So we'll subtract from our 100%. And so we've got 12%. So as a decimal, that's 0.12. So we'll go 1 minus 0.12 and then to the t power. So then again, you can just simplify that stuff inside the parentheses. So we won't be able to bring in this 18,900, but we can do 1 minus 0.12, which gives us 0.88 and then to the t. So remember that this growth factor in here is kind of how much you have left. So here we're increasing, so we have more than 100% because 1.33 as a percent would be 133%, meaning that this is growing. Where this 0.88 as a percent is equal to 88%. So this is decreasing because we have less than 100% left each time. All right, then looking at this word problem, it says an element has a mass of 730 grams, and it's going to decay by 27.6% per minute. How much of the element will be remaining after 12 minutes to the nearest tenth? So we'll want to write an equation first, and then we'll plug in the minutes. So we know that we're going to do P of t equals the initial value, okay, which is that 730 grams. And then we're going to multiply that times 1 minus the rate since it's decaying. And then just make sure that you remember to do your rate as a decimal, so 0.276. So 1 minus 0.276. And then to the t. So then we can simplify if we wanted to. So P of t equals 730 and then 1 minus 0.276 would give us 0.724 and then to the t. So now this one wants us to figure out after 12 minutes, okay, which is what they gave us. They gave us the decay rate per minute. What will we have? So now we're just going to take this function and we're going to plug in 12 wherever we see t. Okay, so we're going to plug in 12 and that's going to go up here as the exponent. And then you'll just type that into your calculator. So we had 730 times 0.724 and then we're bringing that to the 12th power. So we get 15.14208. And this one wanted to the nearest 10th of a gram. Okay, so P of 12 is going to equal 15.1 grams. So after 12 minutes, there's 15.1 grams left. So then when we look at half-life and doubling formula, so if we're looking at half-life, right, it's when this is going to have half the amount or have a decrease of 50%. So in here, 0.1/2 as a decimal is 0.5. So your growth factor is 0.5 or half of the original. And over here in the doubling formula, your growth factor is 2 or it's doubling each time. And then we just have to account for up here the half-life. So it's not just going to be every 5 years or every 1 year. You have to account for how often that's going to happen. It's not going to be every 1 minute or every 1 year or every 1 hour. So you're going to have to take your time divided by the half-life or doubling period. Okay, so this R is now the amount of time it takes to cut in half or to double. So suppose the half-life, okay, so half-life is giving us, that our growth factor is 1/2. So that base value is going to be 1/2. That tells us what function to use. Okay, so we're using f of x is going to equal your initial amount times 1/2 to the t divided by r. Okay, so your initial amount times 1/2 to the t over r. And in this case, they tell us that the substance, the half-life is 20 days. So that's our R. So they're telling us the half-life of the substance is 20 days. And there are 5 grams of the substance present initially. So this is going to be your initial amount is 5. So find the time when there will be 1 gram remaining. So let's write this function. And I guess if I have a t variable here, I should really have a t in this function. But so if we're doing f of t equals the initial amount, which is 5, okay, times 1/2 to the time period divided by the half-life. And remember, our half-life period in this case was 20. Okay, so every 20 days. So here's our equation. Now we're trying to figure out when will there be 1 gram of substance left. Okay, so you can do this by putting this in your calculator. You could just sit and guess and check. I would probably not do that because I don't like to guess and check. But if you wanted, this is going to be how often it cuts in half, right? And we started with 5. So when we cut 5 in half, so after 1 half-life, it's going to be at 2.5. If we cut that in half again, it's going to be at 1.25. Okay, I'm just dividing by 2. And then if I cut that in half again, when I divide 1.25 by 2, I get 0.625. And remember that this half-life, okay, so for it to cut in half takes 20 days. So it took 20 days to go from 5 to 2.5. It took another 20 days to go to 1.25. And then it took another 20 days to go down to 0.625. So it's going to be somewhere in here between 40 and 60 days that this happens. So if you are just plugging in random numbers, make sure you're plugging in numbers that would make sense, somewhere between 40 and 60. Otherwise, in your calculator, you could go into the y equals button, okay, and you could type this function in. So 5 times 1/2, okay, and then in your exponent, if it doesn't move your exponent up like this calculator does, make sure you put a parenthesis up there. Okay, I don't need to because it puts this whole thing in the exponent. So x divided by 20. So now I'm just going to go into my table. So second graph, and I'm just going to go down. And now remember, I told you we looked at it's going to be between 40 and 60. So if I go to window, and actually second window so that I'm in table set, I can change this starting value. So I'm just going to change this to 40 so that when I go to second table, it'll start at 40. So now I can just go down until I see where it's going to be at 1 gram remaining. So that's going to happen on day 47, that it's going to get to less than 1 gram. Okay, at 46 days, it's still more than a gram. So at 47 days, it's going to be less than 1 gram. All right, so let's try another one. So suppose the culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. So they started by putting 100 bacteria in the petri dish. Okay, we know it's doubling, okay, and it's doubling every hour. So let's write the equation for this. So remember, this will be like f of t equals our initial amount. Now it's doubling, so our growth factor is going to be a 2. And then to the time divided by the doubling rate. And so in this case, our initial value is 100. And then we have 2, and then to the t divided by, and then this is every 1 hour. So now you just have divided by 1. And so we want to find out when this is going to be 350,000. So again, this is going to be a pretty big number because you're going to keep doubling. So you started at 100. So we're going to multiply by 2. That would be 200, and then 400, 800, 1600, 3200, and we got to get up to 350,000, right? So this is going to take a while, or it's going to be a bigger number in your table. Now this is only hours. So this is after 1, 2, 3, 4, 5, 6 hours to get to 6,400. But so let's plug this in. So again, we go to y equals, okay, and we'll type in 100 times 2 to the t, or to the x. And then you don't have to put the divided by 1 because that won't do anything. So now we're going to go into our table and we're going to look for 350,000. So you can see in my table right now, I'm way too high because this is at e to the 14th. So this is moving this decimal 14 places to the right. So I'm going to go second window so I can reset my table. I'm just going to put it at something like, maybe I'll put 15 and see what that does. So 15 is in the millions because it's moving that over 6 places. So let's keep going down. And so we see that this one at 10 is 102,000, at 11 is 204,000, and at 12 is 409,000. Okay, so this is going to hit 350,000 sometime after 11 hours. Okay, so after 11 hours, before 12 hours. So somewhere, like 11 and a half hours or whatever, but you can just put after 11, before 12. All right, then I want to do an exponential regression, and I'm going to show you how to do this in your calculator. So the accompanying table shows the number of bacteria present in a culture over a 5-hour period, where X is the time in hours and Y is the number of bacteria. So let's write an exponential equation for this, rounding all coefficients to the nearest thousandth. So now we're going to take and use our calculator to help us get a regression model, or an estimating function. So in order to do this, you need to go into your list. Okay, that's above this stat button. So you're going to hit second stat. Whoops, mine didn't go to it. Oh, I'm sorry. Not second stat. Go into just stat. Okay, let me quit and start over. So go to stat, and then you need to edit. Okay, so select number 1, and then you're going to edit your lists. So now if you have stuff in your list already, you're going to want to clear it out. Okay, so you're going to hit clear. Do not hit delete, or it'll delete your list. Okay, so go up to the top. So when you're here, just arrow up to the top and hit clear. Do not delete. So it's gonna clear out all that data. So then you just push arrow down and then it'll clear out the list. So now you're just gonna want to type all of that in. Okay, so we're gonna type in all of these numbers into our X. We're gonna go 0, 1, 2, 3, 4, and 5. Then you're going to arrow over to list 2 and you're going to type in all the bacteria. So type in 305, push enter, 361, hit enter, 435, hit enter, 515, hit enter, 620, hit enter, and then 697 and hit enter. And then just double check, make sure you typed everything in correctly, because if your data is wrong, your equation is going to be wrong. So now you're going to go into stat again, and this time you're going to arrow over to the calculate menu. Then you're going to want to go down in these REGs right here. So at number 4, it says linear regression. Number 5 says quadratic regression. 6 says cubic regression. You want to find the one that says exponential regression or EXP regression, which is this 10th option, or the 0. So arrow down until you see exponential regression and then hit enter. Your calculator might ask you some options. So we typed the X's into list 1, the Y's into list 2. So that's all correct. So we're just going to arrow down and hit calculate. So now when you do this, it'll give you some numbers here. And you may or may not have these R values in yours. These are diagnostics. And it'll tell you how close your regression is to your actual model. So if they're not turned on, don't worry about it. I don't really need them in this case, but you can see on my screen, the closer this is to 1, the better your model is. So this is a really, really, really good model since it's a 0.998 R value. So in order to write this, okay, so these are the numbers that you got in your calculator. It's giving you the equation. So it's telling you to take A times B to the X. And they're giving you A and they're giving you B. So this one said round all coefficients to the nearest thousandth. This means 3 decimal places. Okay, so I want to round to 3 decimal places. So I'm going to ignore these. And this is going to round the 5 up to a 6 since this is 7. So we're going to make this a 6. Okay, and then this one, we're going to look to the 4th decimal place is a 4, so that's going to leave this one. And then we're just going to write an equation for this. So we're just going to go y equals, and then our A is 307.276, and then times the B value is 1.184, and then to the X. So here's our equation. So now we want to use that equation to determine how much is left after 15 hours. So we just want to plug 15 in for X. So we're going to go back to our calculator and just use our model to do that. So 307.276 times 1.184, and then to the 15th power. So this is how much bacteria is present. And then we'll have to see what it wanted us to round it to. But we have 3,870.8306. And this wanted us to round to the nearest whole number. So after that much time, there was 3,871 bacteria based on our model.